We're going to look at a sine wave again using desmos. So y equals sine t. We're in radian mode, so it makes sense that the wave completes itself in 2 pi radians. 0 degrees, up here is 90 degrees, 180, 270, and 360 when we're in radian mode. That's what I want you in right now. I want to force the wave to complete itself in 1 unit. So to do that, in front of the t, we'll just put in 2 pi. Just type in the letters p and I. And now the wave has completed itself in 1 unit. When t equals 1, sine will have 2 pi. That's the same as 360 degrees. But all that matters now is we have a wave completed in 1 unit at a time, which we can call seconds. Now I want to make more than this. What if I want to make 10 waves a second? What could we do? We could put a 10 in front of the t. Notice though it goes to subscript. It can be very difficult to get it to take the unit where you want it. So our best bet then is to simply go times 10. And now we have 10 waves inside that 1 second. But they're awfully tall and narrow now. So we need to shrink the height down a bit. So I'm going to put decimal 1 in front of the sign. And now the wave is a lot shorter than before in the vertical axis. And we can fit 10 in on the horizontal. And easily see that we've got our 10 waves. The 0 crossing to the 0 crossing is 1 wave. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 waves occurred in the 1 second. So this is really frequency. So I'm going to replace it with the letter F. And Desmos doesn't need it, but just to make it clear, this is going to be the standard wave equation you use once you get to grade 12 and beyond. You will have y is equal to sine 2 pi tf. We're just playing with it right now. Once we've established our small formula here, it stopped plotting it because there are, what it would say, too many variables. We have to create a slider for one of these. We're going to make a slider for frequency. And I want our frequency to go between 90 and 110. And we'll let it pick its own steps. So now if we grab the slider, we can compress and stretch the wave in terms of its frequency. But it's still really tall now, so let's shrink it down in height again. That's a little bit better. All right, now I want to compare it to another wave. We're going to make a fixed wave that has a frequency of 100. So we're going to have a fixed wave with frequency 100. To do that, we're just going to go y equals 0.05 sine. Now what's 2 pi t times 100? It's going to be 200, right? And this is a wave that is going to stay at a fixed frequency, and the other wave can change behind it. Interesting. You see that effect? This is called the Moire pattern. If we get in close, it's easy to see what's happening here. The one wave is shifting. You can have a lot of fun with setting up little things like this. You can see that pattern shift. But we don't really want the wave stacked like that because while it's cool to see that pattern developing, we want to look at it in a bit more detail. But I just thought you might enjoy seeing that. So what I need to do is get these waves off of being on top of each other. So what I'll do is I'm going to move this first wave up. I'm going to move it up to 0.4. So we'll just go 0.4 plus. Should do it. Now it's up out of the way. The other wave, I'm going to move up to 0.2. Now it's up out of the way. We've just shifted it up the axis. And I'm going to add them up on the 0 axis. So I'm going to put these two waves together, but without this leading term. So right in here, I'm going to write y equals 0.05 sine 200 pi t. This is now a dead copy of this wave here, right? And then I'm going to add to it this wave. Go in here, copy that, and I'm going to add it. Now, what we've got is that creepy little pattern that was showing up is now sitting here on its own. This is the addition of those waves. So when I move the slider now, you're going to see the original wave with the slider, this red one here, and the blue one is just added to it, and this is the result when the two waves are added. If I move this slider here till I get right on 100, then the two waves are identical. We have a wave of height decimal 0.5, another wave of height decimal 0.5, and it adds up to a height double as that volume. There's nothing remarkable about it now. Two identical waves added up to a third wave twice as big as both. But if I begin to drift the second wave, not keeping it at 100 pulses per second, but I increase it or decrease it, something funny starts to happen. These spots of cancellation appear, and we want to see what's going on there. And then they reappear this way. So the spots are they're going from cancellation. So let's do this right here. Let's move this slider so we can get a cancellation spot. There, looks good. And I'm going to zoom in, bring this down, and we're going to try to take a look at what's going on here. I'm just obsessed with getting it right on the axis. That's pretty close. Why have the waves added to 0? Well, let's shift this one down a little bit. It's up a little high. I want to bring it closer to the red one. So let's just try 0.3. There we go. That's brought them nice and close to each other. Let's zoom in here. The only way these two waves could have added up to 0 is if they were in opposition to each other. And sure enough, when we zoom in here, we can see that as this red wave was at its maximum, the blue wave wasn't at its maximum. It was down at the bottom. So it totally canceled. Now, if we start sliding over, you see there's a drift. The blue wave's lowest number is no longer corresponding with the red wave's highest. And as we slide over, they're drifting. And that's because they're slightly different in their rate, their frequency. And it gets to the point where if we keep going here, it's looking pretty close that at this point in time, the red wave is at its peak and so is the blue wave. If that's true, the addition of the wave should be at its maximum. Let's see. Right there. Look at that. Where we found crest meets crest, we found an area of maximum constructive interference. When this happened here, if we examine the source wave, trough meets trough. So if two frequencies are slightly different from each other, they will cause this pattern to develop where they'll briefly constructively interfere and then destructively interfere. And the rate of that event changes the more the frequencies are different. At this point in time, the frequencies are different by 10 hertz. So this means the one frequency pulses 100 times a second and the other one does 90. So they'll line up more frequently. As their frequencies get closer and closer together, the lineups become basically permanent. And now they line up less frequently, but they still occasionally line up. But you get this very weird pattern called the beat frequency. And we're going to stop and take a look at what it is on Audacity. Now that we're in Audacity, we're going to generate a track. Generate, tone, and I'm going to pick 220 Hertz. No problem. Now we're going to generate another track, and we're going to select this track only. So I click on it, and then we go generate, tone, and this time we're going to generate 225. I'm going to solo this track. Get the idea? Now I'm going to do Control A. That selects them both. And I'm going to go Tracks, Mix, Mix and Render to New Track. And this is the addition of the two sounds together. I'm going to delete the original tracks, and we're going to listen to what it sounds like when they're mixed. What's going on there? Let's zoom in. It looks like we're getting what are called beats again. We're getting the same pattern from the other program, Desmos. But it's a mess. It doesn't look clean. So we're going to have to go backwards here. Let's do an edit, undo, track, remove, edit, undo, track, remove, edit, undo, mix, and render. We want to take these tracks and add them up without them exceeding the volume limit. So we'll take this and move it down to, say, -15 on both of these. Doesn't really matter what. Now do Control A, tracks, mix, mix and render to new track, and it's not nearly as loud. But just to convince you that the two sounds separately make this noise. There it is. Now, what's going on in here? We can get a thing called aliasing. So I'm going to go in here and zoom in. Those are the waves. If you back out too far, you won't see the waves anymore. You'll see these weird patterns that have nothing to really do with the waves we're looking at. It's a feature of your monitor. So we have to be careful to make sure we're seeing the waves, not this moire effect. So I'm going to zoom in a bit more. Now we're seeing what I'm after. You can see the up and down action of the waves here, the up and down action of the waves here, but there it is. There's the lump, 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 and that's the beat frequency. That's how you can tell two waves are out of tune with each other. And you hear that wah, 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 wah as the moments of constructive interference. Now, we can do this with numerous waves, but you'll find the further they are apart, this pattern eventually disappears. But for right now, you can create these patterns and see and hear the effect of adding two waves of slightly different frequency. Using my favorite drawing program, CorelDRAW, I can set up a basic Moire pattern here by using two identical grids. So I have two grids here that you can see if I slide one over. And oops, got them both selected. There we go. Two identical grids. And if I slide them by each other, you'll start to see this Moire pattern appear and disappear. It's more pronounced when I line them up and I rotate them. So if I click again so I can rotate, you can see that banding forming. And even now your brain starts to see stripes that aren't there. And this is an interference pattern, which is part of this unit, but it's a visual one, not a sonic or sound. And so we're going to play with these as well, because they're really nifty. Now, if I make the pattern a bit larger, You may even see Moire patterns on the screen, even though there's nothing overlaying it, because your screen itself has a pattern. So I'm going to take this pattern, duplicate it, and then start sliding it down past itself. And you can see that this alternating pattern as the two identical patterns pass by each other. So far, nothing terribly exciting. And you can still see that there are two patterns here when I shove them to the side. All right, and so this Moire pattern is a creation of a new pattern from two overlapping patterns, and it can create something that isn't really there to be observed. So when we look at waves on screen, we have to be careful to make sure we're actually looking at the wave and not an artifact. Well, if you want to see funky, watch this. Let's get it set up for rotate and try again. Now, I'm just going to go up. Whee! Isn't that trippy? Watch right here though. This pattern is simply moving upwards. It's only moving vertically. It's not moving horizontally at all. That is a complete artifact. And yet this pattern emerging is exactly like what's called the single slit experiment next year. And so it's a lot of fun to create patterns on screen and watch this effect develop. And there are online Moire generators, so you will do your physics homework.